Welcome class to lesson 8.3 for Calc 2. Today we're going to look at trigonometric integrals. So we're going to take a look at what happens if we have these funky integrals involving some random combinations of sines, cosines. We'll also look at ones with tangents and secants, how we can simplify those down to do an integration. We're going to use a couple rules here. The first rule is if we have a product of a sine function and a cosine function, we're going to consider case 1 if m is odd, so there's an odd number of sine functions. We're going to basically take out a sine function using the 2k plus 1. We're going to use the identity for the sine squared, that is 1 minus cosine squared. And basically what this next line is telling us, then we're going to set up u to be cosine, and then du is going to be negative sine of x dx. So that way we can cancel the sine and we can come back and do our integration with what's left. We'll do the same thing in case 2. Now if we have an odd number of cosines, we're going to basically pull out a cosine and use the identity cosine squared equals 1 minus sine squared of x. And then that's going to leave us with a sine squared and a cosine, or an even number of sines. Therefore u will be sine of x, therefore du will be cosine of x dx, and that will allow us to cancel out this cosine that will be in the integral. The last case, if they're both even, then we're going to substitute using these trig identities for sine squared and cosine squared, and we'll look at one of those in the upcoming problems. Later on, we're going to do something similar with tangent and secant, but as I said, we'll do some examples of those later. Let's look at some examples. Example 1, we want to evaluate the integral of sine x cubed times cosine of x squared. Notice here we have an odd number of sines. Therefore, we are in case 1 because m is odd. Therefore, we're going to basically take out a sine. So here are 3. We're going to turn into basically 2 times k plus 1. So we're going to integrate. We're going to split this up into a sine squared of x times cosine squared of x times sine of x dx. Now we're going to use our trig identity for sine squared. And the trick here is we're going to turn these into all cosines, using a couple tricks here. So the first trick is sine squared. We can use our trig identity. So now we have the integral of sine squared then is 1 minus cosine squared of x times our cosine squared of x. And then we're going to use a trick here to get rid of sine of x dx. And that is because we're going to all cosines, we're going to set u equal to cosine of x. Therefore, du, the derivative of cosine, recall, is negative sine of x dx. But we want to get rid of the dx at the end of our integral. So dx then is going to equal to du over negative sine of x. So I'm going to leave this as a sine of x dx, but notice here what we're going to do. We're going to replace then, we're going to substitute in dx for du over negative sine of x, and that will get our sines to cancel, and we'll look at that in the next line. So now we have the integral of 1 minus cosine squared of x times cosine squared of x. And again, what's going to happen, we're going to replace our dx with du over negative sine of x. Therefore, the sines will cancel, and we're left basically with a negative dx. Whoops, not dx, we substituted in, so that's du, excuse me. Now we can simplify. So we're going to multiply all of these together. So now we have the integral of, we have a 1 times a cosine squared. And I'm going to backtrack a step. Because we have our u as cosines, now we can switch to our u variable. So we're going to plug in all of our u's. So now we get 1 minus u squared times u squared times negative du. Now we can come back and simplify. So we have a 1 times a u squared times a negative. And that will be a u squared minus u to the fourth times du. And now we can come back and integrate. We'll add 1, divide by 3, so we get a, and I think that negative should have gone out to the front. So now we can integrate. We'll get negative u cubed over 3, plus we'll add our 1 to the 4 to get 5, divide by 5. And then plus c, the sign's flipped because we have the negative for the integral. Now we can come back and plug in our u, which is our cosine, to get our final answer, which then is negative cosine cubed of x over 3 plus cosine to the fifth of x over 5 plus, don't forget, our constant of integration. So again, a couple tricks we did there. We got, because sine was the odd one, we're going to make it down to be even. Now we can make a sine of x, again, turn back into our du, so we can substitute with our cosines to turn this all into u's, so we can make the integration possible. Let's look at a case 2 problem. Here we have a cosine to the fifth of x. So again, this will be a case 2. So we're going to pop out a cosine to get the integral of cosine to the fourth of x times cosine of x dx. But for our property to work, we want this to be in the form of 2k plus 1. So we're going to make our cosine to the fourth x be a cosine squared of x quantity squared times cosine of x dx. And again, we're going to set, and we're going to use our identity for cosine squared of x. So we're going to have the integral for cosine is 1 minus sine squared of x quantity squared times cosine of x dx. And again, here we're going to set for u, because we have a single cosine, that's going to be our du. So we're going to set u equal to sine of x. Therefore, du is equal to cosine of x dx. And that will then allow us to substitute in our cosine of x for du. So now we can do some substitutions here. So we have the integral of 1 minus, our sine of x is u, so we have 1 minus u squared, quantity squared, times, again, our cosine of x dx, then is our du, making that substitution. Now we can do some simple algebra to simplify this out, and when we FOIL that out, we get 1 minus 2u squared plus u to the fourth du. And we can use basic integration to do that. So integral of 1 is u. The u squared will add a 1 to get 3, divided by 3. It leaves us with negative 2/3 u cubed. We'll add a 1 to the 4 to get 5, divide by 5 to get 1/5 u to the fifth plus c. Now we can plug back in our original u of sine x, and we get our final answer, sine of x minus 2/3 sine of x cubed plus 1/5 sine of x to the fifth plus c. That leaves us to look at a case 3 problem, and this one's going to be very long. You want to take the integral of sine squared of x cosine to the fourth of x. Notice here they are both even, which qualifies us to be in case 3. When that happens, then we're going to use a trig formula, and that is we're going to replace sine squared of x with the trig identity 1 minus cosine of 2x all over 2 times 1, and then we'll use the identity for cosine to the fourth x, which we're going to rewrite as cosine squared of x quantity squared. 1 plus, that identity is 1 plus cosine of 2x over 2 quantity squared dx. From there, we can look to simplify, and the first simplify we're going to do is we're going to multiply out this top term. So we have the integral of 1 minus cosine of 2x over 2 times, we'll FOIL out the top and square the bottom. So that's going to give us 1 plus 2 cosine of 2x plus cosine squared of 2x all over 4 dx. Now we can simplify that out a little bit by multiplying. We're going to pull the 1/2 and the 1/4 out to the front as a constant of 1/8. That will leave us with the numerator, so we're going to multiply this numerator times this numerator, doing a lot of multiplications, and that's going to leave us with 1 plus 2 cosine of 2x plus cosine squared of 2x minus cosine of 2x minus 2 cosine squared of 2x minus cosine of 2x cubed, again all in dx. That will allow us to do some simplifications. Notice here we have a couple like terms. 2 cosine of 2x minus cosine of 2x will simplify. And so now we can simplify this down to 1/8, the integral of 1 plus, again this 2 minus the 1 will leave us with 1 cosine of 2x minus cosine squared of 2x minus cosine cubed of 2x when we do all of our simplifications dx. Now we can simplify. Now we can start working through our integrations. The first two terms will integrate normally. The second two terms we're going to use a u substitution. So we're going to end up then with 1/8 times the quantity. The antiderivative of 1 will be x. We know the antiderivative of cosine would be sine of 2x. But remember, we have to divide by the differential of the argument. So the derivative of 2x is 2. We need to divide by that 2. That leaves us then with minus the integral of this term, these two terms, cosine squared of 2x minus cosine cubed of 2x dx. We can take care of these. We're going to use... we can take care of the first one using just u substitution. The second one, we're going to break that down to be a cosine squared of 2x times cosine of 2x. And then we're going to use our identity, our cosine squared identity on that one as well. The substitution we're going to use will be u equal to and apologize, we're going to also use a double angle identity on cosine squared of 2x. So I'm going to leave this first part out for a while, and we're going to tackle this second integral. So now we get the integral of cosine squared of 2x. We can use an trig identity, and that trig identity for the double angle of cosine squared is 1/2 times 1 plus cosine of 4x dx, plus then the integral using our Pythagorean identity for cosine squared. We're going to get then 1 minus sine squared of 2x still times our cosine of 2x dx. I think I missed a parenthesis in there. So still leaving that front half part, that then is going to give us, now we can do our integrations. So minus, we have the integral of 1/2 times 1. That's just going to be a 1/2 x. The antiderivative then of cosine is sine of 4x. We need to also then divide by 4 times by the 1/2, then gives us, and with the minus outside, gives us a minus 1/8 times sine of 4x. Now we can then tackle this last integral. Note here, this is going to be after we do our multiplies, and I lost an integrand of 1/2. We're going to do a u substitution for this one, and that is u is equal to sine of 2x. Therefore, du is equal to the derivative of sine of 2x, then would be the 2 comes down and multiplies by the sine of x times the derivative of sine of x, which is cosine of 2x. Cosine of 2x. We're going to plug that in. So now we get plus 1/2 the integral of 1 minus u squared du, which then becomes plus then 1/2 sine of 2x minus 1/3 sine of 2x cubed. So now we can put all of that together. Starting back up from up here, we have then 1/8 times the quantity, our x plus 1/2 sine of 2x minus 1/2 x minus 1/8 sine of 4x minus 1/2 sine of 2x minus 1/6 sine of 2x cubed. We can do some canceling here. Minus 1/2 sine x and 1/2 sine of 2x cancels to leave us then with 1/8 times the quantity, 1/2 x. We can also do some like term combining as well. So 1/2 of x minus 1/8 sine of 4x minus 1/6 sine cubed of 2x. And then our final answer, as we multiply out, or we can actually factor out a 1/2 out of all the fractions to leave us with the book answer, 1/16 times x minus 1/4 sine of 4x minus 1/3 sine of 2x cubed. And as always, don't forget your plus c. You can follow that through the book as well. That's a big, long problem. Lots of stuff going on there. Next trick is to eliminate a square root. So in the example, we're going to use another trig identity, and that is that cosine squared is equal to 1 plus cosine of 2 theta divided by 2 to eliminate the square root. So we're going to notice that 1 plus cosine of 4x is going to match our identity. So we're going to start with cosine squared of theta is equal to 1 plus cosine of 2 theta over 2. Notice there's not an over 2 here. So we're going to multiply the 2 to get cosine squared of theta. So we're going to change our identity a little bit. It's equal to 1 plus cosine of 2 theta. Well, here notice that matches. Our 2 theta then has to be equal to make this work out correctly and match, we need basically a 2 times a 2x here. So our 2 theta is going to equal, let me back that up. Our theta is going to equal to 2x to make it work out correctly. Therefore, our 1 plus cosine of 4x, we're going to turn that into our identity, basically go in this direction, 2 then times cosine squared of 2x. So now we're going to, instead of integrating this function, now we have a new function, and that is the integral. And we're still in x, so we don't have to change our bounds of integration. 0 to pi fourths times the square root of 2 cosine squared of 2x dx. And that works really nicely because now we can square root and get a constant square root in front times the integral of, that leaves us with a square root of cosine squared of 2x, which leaves us just with then cosine of 2x dx, which we can integrate really easily. And so that's going to be then from 0 to pi fourths, then the square root of 2 times, and the antiderivative of cosine is sine of 2x. Again, we need to divide by the du, so the derivative of 2x is 2, so we need to multiply that by 1/2 or divide by 2, and we're going to evaluate that then between 0 and pi fourths. That leaves us then with root 2. I'm going to pull this 1/2 out as a fraction to be 1/2 times 2. Therefore, we can plug in sine of 2 times pi fourths would be sine of pi halves, sine of 90 is 1, minus, plug in our 0, sine of 0 is 0, and that leaves us with root 2 over 2. And again, you can double check that using your calculator. Takes us to example 5. So we can do this similar thing with tangents, integrals with tangents, recalling that the derivative with respect to x of tangent of x is secant squared of x. So here our goal is going to be, we want to try to get secants, therefore we can set u equal to tangent of x, and therefore du then can be our secant squared of x, dx is going to be our goal. So we're going to do that, we're going to use the identity, tangent squared of x is equal to secant squared of x minus 1, and secant squared of x is equal to tangent squared of x plus 1. And so here we go. So we're going to replace tangent to the fourth of x with integral of tangent squared of x times tangent squared of x dx. That's going to be the integral. We're going to replace one of them first. So we'll do the second one. So tangent squared of x, replace tangent squared of x then with our secant squared of x minus 1 dx. Now we can split this up into two separate integrals by doing some multiplying here. So now we get the integral of tangent squared times secant squared dx minus the integral. Now we have tangent squared of x times minus 1. The minus came out as the minus in front of the integral. So we have tangent squared of x dx. We don't have a good formula for a way to integrate tangent squared, so we're going to switch that back into a secant squared as well. So now we're going to get the integral of tangent squared of x, secant squared of x, minus the integral. Then we're going to switch tangent squared back into secant squared of x minus 1 dx. So now finally we can integrate this identity, doing one more simplify. We have the integral of tangent squared of x secant squared of x minus the integral secant squared of x dx, and then minus the negative gives us plus the integral of 1 dx, or just dx. So now we can differentiate. To do this, for the first one, we're going to set up u is equal to tangent of x, therefore du, and here's where our method comes in, is secant squared of x. So that turns tangent squared into a u squared. Secant squared of x dx then will cancel to be du. We can integrate that u squared to get then u cubed over 3. Plugging back in, that then will be tangent cubed of x over 3 minus the antiderivative of secant squared. There's our tangent of x. The antiderivative of 1 is plus x plus c. So again, the goal there is to get tangents and secant squareds so that we can use u substitution to integrate. Example 6. So now we have a secant cubed of x. Again, we want to try to get to tangents and secants. And so we're going to rewrite this one as the integral of secant of x times secant squared of x dx. And instead of going straight to a trig identity on this one, we're going to use integration by parts. And for that, we're going to set u equal to secant of x, and that leaves then du is equal to sorry, I got ahead of myself. We are going to use our identity. No, we're going to use integration by parts. So, sorry, our d, I got messed up in my notes. Du is equal to then secant squared of x. Therefore, du, the derivative of secant, is tangent secant, or secant tangent, whichever way you want to write that one. So secant of x times tangent of x dx. Then u, when we integrate, turns back into tangent of x. Now we're set up for integration by parts, which recall is u times v minus integral v du. So we get u times v will get us secant of x times tangent of x minus the integral v times du, or v, call that du, that's supposed to be dv, or v, then is tangent of x, or du then is secant of x times tangent of x dx. We can simplify that to get then secant of x, tangent of x, minus then the integral. Now we get a tangent squared times secant of x dx. Now we can use our trig identity for tangent squared of x. So that's going to leave us then with secant of x, tangent of x, minus the integral using our identity. That will give us then secant squared of x minus 1 times secant of x dx. Again, we're going to split that one up so that we have, and we're going to start with the minus first. So a minus times a negative 1 times secant gives us then a plus integral of secant of x dx. And then a minus times secant squared times secant gives us minus the integral of the secant cubed of x dx. From there, we're going to notice, if we have presence of mind, to notice this integral is the same as what we started at on the original. So we're going to add that back to the front of our equation to get, now we have two integrals of secant cubed of x dx. That is equal to our secant of x, tangent of x, plus we still need to integrate then secant of x dx. For that, we're going to use our formula that is in the back of the book for secant, and also we're going to divide by 2. So that leaves us then with our final answer. When we divide by 2, we get 1/2 secant of x, tangent of x, plus 1/2. The formula for the integral of secant of x is the natural log of the absolute value of secant of x plus tangent of x, and as always, don't forget your plus c. That takes us to example 7. Here we're going to integrate tangent to the 4th of x times secant to the 4th of x. Again, here we're going to use some trig identities to help break us down. Our goal here is again to get something in the form where we have tangents to an even power, and then that leaves us then with secants squareds of x to be our u. That way u can be tangent, and then du is going to be our secant squareds is our goal. But right now we have secant to the 4th, so we need to break this down again using some trig identities. So we're going to start with the integral of tangent to the 4th of x. We're going to break secant squared into 2 secant squareds using an identity on the first one to call that 1 plus tangent squared of x, still times a secant squared of x dx. From there, we can do some multiplying through. To get the integral, we'll multiply the tangent of 4 through, so we get tangent to the 4th of x plus tangent of x to the 6th power times secant squared of x dx. Now we can split those up to get the integral of tangent to the 4th of x times secant squared of x dx plus the integral of tangent to the 6th of x, or the x to the 6th power, times secant squared of x dx. We can actually tackle both of these then using our strategy up above. We're going to set u equal to tangent of x. Therefore, our du has to be secant squared of x dx. So this turns into then the integral of our tangent to the 4th of x turns into u to the 4th. Secant squared of x dx turns then into du plus our integral. Now we get u to the 6th power our secant squared of x then again turns into du. Now we can use that we can integrate using regular integration rules. So that would be u to the 5th over 5 plus u to the 7th over 7 plus c. Plugging back in our original u of tangent gives us then 1/5 tangent to the 5th of x plus 1/7 tangent of x to the 7th power. And again, don't forget your plus c. Next step takes us to the formulas for the products of sines and cosines. Where here we have a sine and a cosine function with a power of 1, but there can be constants inside the arguments. So an m and an n, where m is the first constant in the argument, n is the second constant in the argument. And there's derived formulas for us to use. We'll look at one of those examples. For example, 8, we're going to evaluate the sine of 3x times the cosine of 5x. Because sine and cosine are both to the power of 1, we can use that formula. And so here we go. So referring back to sine and cosine, we're using this formula here for sine and cosine. 1/2 times sine of m minus n of x plus sine of m plus n of x. And here we go. So this turns into then 1/2 times sine of, subtract the first minus the second constant, is 3 minus 5 of x, plus sine, now we're going to add the constants to get 3 plus 5 of x, quantity dx. We can simplify those arguments then to get, and pull out the 1/2 to get the 1/2 the integral times sine of negative 2x dx plus sine of 8x dx. Dx is not supposed to be there because we want a parenthesis there. Now we can integrate, so we have 1/2 times the quantity. The antiderivative of sine is negative cosine. The argument stays the same, so that's a negative 2x in the argument, divided by the du. So if u is negative 2x, we need to divide by a derivative of negative 2x is negative 2, so divided by negative 2. Those 2's then cancel, those negatives cancel, plus the antiderivative of sine is negative cosine. The 8x stays the same, but we need to divide again by the du, so the derivative of 8x in the argument is an 8. Again, plus r plus c. Now we can simplify by multiplying by through the 1/2. That leaves us then with cosine of, and we can do one other simplify here, and that is using the identity that cosine of negative theta is equal to negative cosine of theta, because cosine is an even function. So we get negative cosine of 2x over 4 minus cosine of 8x over 8 plus c. That is using trig techniques for integration.